So, thank you for accepting our invitation to deliver the lecture on the extreme wave impact on buildings defended by Seawall. Definitely, it will be very useful to our students. So, we have started this MTech Ocean Technology. Previously, it was MTech Coastal Management was offered from 2007 to 2020. The 2 years it was suspended, and then again 2023 we have started MTech Ocean Technology. So for the past 2 years we are offering the MTech Ocean Technology. So the first set students they are now doing their project, and the second set of students they are in the second semester. Next month it will go up to May, and they may go for an internship during June, July, and all. So this is the thing. And in the curriculum we have, you might have seen the curriculum. Otherwise, we will send you the curriculum also.
Yeah, that would be better, ma'am.
Yeah, yeah.
I have a rough idea of about your curriculum, but
Oh,
I'm not sure about the revised one because I knew about the coastal management courses.
yeah, yeah. So we will send you the revised curriculum for MTech Ocean Technology. So the
Mm-hmm.
students they are doing a project in NIO Goa, NIOT, and then NCSM, DHI, like that. We have sent the for different organizations. Our students they are doing their project work in different places.
Mm-hmm.
So this is the status, and only two seniors students have come, and there are first batch 7 students are there, and some research scholars also attending, and one DST scientist, woman scientist also attending your lecture. So we will go over to you. Okay. So and then
Thank you.
another thing is we have Anna University given the advertisement for recruitment, and this time
Mm-hmm.
we have added coastal and ocean engineering specialization.
Okay.
Be civil with the ME or MS, MTech, and with PhD. This is for
Okay.
your kind information. Huh?
Thank you very much for informing me.
Yeah.
Also, I just wanted to check, are there some PhD students sitting here or?
Yeah, yeah. He's Sudarshan. Sudarshan, he is doing his PhD on sea level rise due to climate change and it impacts on coastal infrastructure and community. Another one, he is going to register on mangroves mapping using artificial intelligence and the tidal impact of micro mangroves. He is going to register that one. And
Mhm.
two of them, they are doing it NIOT on
Okay.
wave climate in the northern Bay of Bengal, northern central Bay of Bengal. Like that, they are doing the PhD. Here only Sudarshan is here, and another two are related to water resources PhD.
Okay.
So that is about PhD. Hello, that's all. And we are running one ministry project in that we are doing the outreach activities and all. So many outreach activities. Okay, this is
Yes.
a brief introduction.
Okay. Thank you very much, ma'am. And at first, before I start with, maybe I'll also check whether my screen sharing is working fine. Can you see my screen?
Very small it is. Now, half an hour. ಅದು ಕೂಡ தேவையிಲ್ಲ யூஸ் பண்ணிடுங்க.
Yes, sir. Screen is visible, but like you can
Okay.
get the window presentation, sir, for full screen.
Okay.
Ah,
இந்த சைடு ரெண்டு இது வேண்டாம். That is இந்த ரெண்டு
yes,
இது
yes.
வேண்டாம்.
Okay.
So that அவரோட அந்த
So now the screen is not visible. It has gone.
Now?
Now the screen is not
லைட்
visible.
ஆஃப் பண்ணலாம்ப்பா.
Ah, yes.
Is it fine now? I'm in the presentation mode now.
Yes, sir. The screen is visible, sir.
Okay. So do you also see my slide changes or
Yes, the slide change is also clear.
nice? And is it working fine or should I make some changes?
Sir, give slideshow, sir. Press F5 or like bring slideshow, sir.
No, 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 it is already in the slideshow mode, but I'm not sure like why it is.
It is like on PowerPoint when we open, no, sir, that screen is only visible.
Yeah, 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 yeah. I can understand, but yeah, maybe I'll do this way.
Okay, sir.
Maybe what about now?
Yes, sir. Now it is clear.
Super.
Yeah.
Okay, ma'am, can I start or should I wait?
Yes, sir. You can start.
Can we start? Okay, super. At first, yeah, okay. Let me start. At first, I would like to thank Professor Krishnavani Muttaya for inviting me for the webinar. In fact, like my contact was established with via LinkedIn, and later I approached her so that like we could work on some joint projects or something. And Professor Krishnavani Muttaya offered me a webinar session, which I'm really grateful of. And thanks to Mr. Sudarshan for arranging everything. Now I hope like now everything is working fine. So let me also quickly start with the basic introduction of me, as well as the projects which I'm working in this institute at the moment, so that like it will also give some clarity about what we are doing, and maybe in future like we could find some joint research works and yeah, joint activities of our similar kind. So the topic of today's presentation is on extreme wave impact on buildings defended by seawall. Of course, it is a part of my PhD research work, which I carried out as a joint doctoral student between the Indian Institute of Technology, Madras, which is just opposite to the Department of, just opposite to Hana University. I started my career in the Indian Institute of Technology around 2017, the beginning of 2017, as a master student. Previously, I was working as a project officer there. Then later, around 2018, like upgraded my master's degree to a PhD degree. And after working there for 1 year approximately, I had an offer to go to Germany as a joint PhD student, which I was like really happy about it still now. So from 2019, I started working at the Institute of Hydraulic Engineering and Water Resource Management, RWTH Aachen University, as a joint PhD student between IIT Madras and RWTH Aachen. And later, by the end of 2022, I submitted my PhD thesis, which is on tsunami interaction with shoreline structures. And in the year 2023, I defended my PhD, and now I'm working as a joint. I'm working as a postdoc here, and also leading a small research group here, which is on coastal engineering. And yeah, where exactly my research institute is. So as you might know already, that like Aachen is located in Germany in the state North Rhine-Westphalia, and our city specifically is bordering two countries, nearby countries, which is Belgium and the Netherlands. And this is my research institute here, and I work under Professor Holger Schifrumpf, who is the university professor here. And unlike Indian universities, in German universities, like we have only one professor for the entire institute. And my professor works on various topics related to water, starting from coastal engineering to inland floods, for example. And I don't know. Oh, okay. So to give a basic idea of like what all the scholarship may be available for the master students as well as for the PhD students, maybe if they want to continue their studies in Germany as a guest scientist, for example, in some research institutes, maybe TU Dresden or TU Berlin or maybe even RWTH Aachen. There are several such scholarships available between India and Germany. So I had I had a good opportunity to get several scholarships for my stay in Germany. So this is something for you. And in addition, like IGCS and ABCD Center, so the both are set up at IIT Madras, and they are providing opportunities for joint research activities between various research institutes in India and Germany. Probably it is something for your interest maybe in future if someone wants to apply. And besides, I also wanted to give a basic intro of what I was doing for the past few years in this research career. So I had an opportunity here to guide a few master students and a bachelor students on several topics related to tsunami interaction with building, tsunami debris impact on structures, and also I was focusing on evaluating the effect of vegetations in reducing the tsunami inundation energy, and also I had opportunity to work on topics related to underground pump storage reservoirs, which is more or less equal to conventional hydropower plants, but here in the lower reservoir of the hydropower plant is located underground. And in addition, recently, like I started also working on several topics related to wave overtopping, and currently one of our master students is working on a dual gauge simulation of a wave overtopping the vertical seawalls at convex and concave bends. And besides, like I also started working on topics related to flow around spur dikes, river spur dikes, for example. So this is something to give a basic intro of what I was doing, what I am doing at the moment. And in addition, like as a group leader at this institute, I also supervise some of the PhD projects here. So I listed few. I listed all the PhD projects which I'm currently kind of responsible here. But of course, like I'll not be the main supervisor, but I'm kind of co-supervising. So several topics. We also work on several topics more related to fundamental research on have water flows, and also we focus on flow overtopping the dikes. The dikes are more common in the coasts of Germany, Netherlands, and even Japan, and a few other countries, even in Asia, for example, in Vietnam, Singapore, for example. So there, people always also choose dike in besides seawalls, and there are some students who are also working on effectively reducing tsunami wave energy reductions. Also, I also focus and interest on have interest on wave impact propagations and several topics. Also, these are all some research projects which I have been working at the moment and worked at the past. So one thing which I was also focusing on is in the past, which was completed just 2 months before, was on assessing the tropical inland floods due to precipitation in the Cameroonian region, Africa. So overall, this is a kind of a detailed overview of what I was doing and what I have been doing for the past few years. And now I would like to go with the topic of today's lecture, which is on extreme wave impact on buildings defended by seawall. So when you start thinking about extreme waves, like people start tend to think about none other than tsunamis. Like after our experience of 2004 Indian Ocean tsunami, so people always think extreme waves means like tsunamis. And in addition to tsunamis, like there are several other factors happening at the coast. For example, storm surges, and sometimes even a landslide generated tsunamis and coastal floods. Yeah, of course they are kind of rare events, but once they occur, like they induce a devastating effect at the coastal region. So also I highlighted some numbers here, like which is 227,898 and 15899. So these are all nothing but the number of lives we lost during the past events. For example, during 2004 Indian Ocean tsunami and the 2011 Tohoku Oki tsunami in Japan. So you could imagine about like you could imagine how disastrous these natural events are. So once such event occurs, for example, like the tsunami waves, when you think about tsunami wave, once a tsunami wave happens in deep waters, like what happens is like the tsunami wave propagates inland, and also it inundates the coast. And in many regions, before I start with it, I would like to play a short video, but I'm not sure like whether the audio is uh, okay for you. Can you maybe hear this audio?
Sir, audio is clear. Yes, sir.
Okay, nice. Probably you would have now heard that like in Japan, like during the 2011 tsunami, they had a huge seawall of a height maybe 18 feet, and in fact the tsunami waves which occurred at the Japanese coast overtopped such a huge seawall and then impacted several buildings at the coast. So when you think about saving the lives of the people, what you could also do is like, in addition to improving the coastal protection strategies, we could also improve the inland structures, for example, and make it as a tsunami resilient structures. But in the past, it was not. So you could also see here that like in the past, in the 2011 Japan tsunami, like almost 400,000 billions, 400,000 buildings were completely, demolished or damaged, severe structural failure during such an event. So if, for example, such buildings were designed for such a huge aerodynamic load, what would have happened? People could have sought shelters on their rooftop and could have saved their life, but it was not the case. So that's where my PhD topic also arises. So I was working completely on understanding the tsunami interaction with the buildings. In addition to it, a part of my research also focused on identifying better solutions to reduce the forces acting on the building, because one cannot design a building for a 10-meter wave height, 10-meter inundating tsunami bore, or tsunami flow velocity of 10 meter per second. So that is would result in practically impossible construction. So when you so that's why like we should also think about protecting our coast in a better way, so that like your buildings experiences least force. Of course, like you cannot build everywhere like 10-meter seawall and then protect your entire coast from tsunamis. So 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 that's where like several solutions came up. The solutions which also include maybe improving the seawall design for reducing the tsunami inundations, or growing green, for example, like growing vegetations at the coast. If you also have a mangrove forest at the coast, then it would also facilitate the reduction of wave energies, because the mangroves in the past were able to successfully reduce the tsunami energies also. And in addition, one could also think about integrating several solutions together. So which comes to my one thing which comes to my mind is like integrating the existing coastal protection structure called maybe seawall, and maybe with in a soft vegetation methods. So that would, by that way, give a double defense to your coastal region. But the cost of such solution would be, you need sufficient space to implement. For example, for seawall implementation, you might need like 10 meters or 20 meters, and for vegetation, you might need like 100 meters. So 100 to 200 meters in order to effectively reduce the tsunami inundation. But one should also not forget that, like, for example, you cannot do this at the Marina Beach, for example, because the Marina Beach is actually known for its aesthetics beauty. But when you start up building up such a structures with a view of protecting against the tsunamis, then there will be also additional conflicts at the coastal regions. But anyways, in addition to that, like there are also several possibilities that, like, for example, introducing buffer blocks. So these buffer blocks, for example, they do not need to be like constructed so tall, but they can be of smaller height. But when you construct it, for example, like in a rows, for example, something like this here. So what could happen is like if it would effectively reduce inundating tsunami energy. So that is another concept. But in addition to it, like we could also think about offshore breakwaters. So several solutions possible, but one solution which I was more interested is also trying to understand the existing seawall or maybe the new seawall designed for reducing the tsunami inundations. Although, like in the video, like you might have seen that like the 18-foot seawall was overtopped by huge tsunami waves, but even in the overtopping conditions, like they still offered in the past. The past studies showed that like they still offered sufficient protection to the coast. For example, they reduced the loading on the building. So that was something observed in the past literature by these two people. So by that way, like now that you can imagine that like a seawall which is located at the coast now have an efficiency to reduce the tsunami force. It is not like completely eradicating, but just kind of reducing. So when you think about the seawalls at the coast, we could think about a vertical, simple vertical seawall, something like this, or maybe introducing some parapets at the top. Introducing parapets or maybe recurve on the top was usually preferred, or still now like it is usually preferred because the reason being is like for a normal wave condition, this introduction of recurve helped in transferring the deflected wave directly to the sea. By that way, the wave overtopping is reduced, which is a major problem at the coast. But nevertheless, there is no study which focused on what happens when you have a recurve during a tsunami-like conditions. So there came my study of trying to first understand what happens when you have a vertical seawall and when you have a vertical seawall with a recurve at the top on reducing the forces on the building behind. So this is a part of my PhD work. And when you think about simulating tsunami in the laboratory, so people thought of different technologies. For example, like one could simulate tsunami by sliding blocks, or maybe using some long wave generation facilities, or using dam break technique where people store some significant amount of water and then they simply release it so that they resemble like kind of a tsunami inundation. And some other techniques like vertical release or using suction pressure methods, several methods available. And in our facility, in our institute, like we have this facility which is a pump generation, wherein you have a control of the discharge which is generated in the flue. And one could in our experimental laboratory we could also generate bore of different conditions by varying the still water depth at the representing the coastal region. But in this specific study of extreme waves defended by seawalls, so I used the dam break technique, which was conventionally adopted for generating tsunamis. So for doing that, like I used a numerical tool called the OpenFOAM. Probably many of you might know already, or maybe for something new to you. So OpenFOAM is nothing but a flow solver for a Reynolds average Navier-Stokes equations. So which is used to solve fundamental fluid dynamics problems. And in this specific case, like I used a solver called Interfoam. So the Interfoam is like basically to simulate the free surface flow consisting of two phases. For example, herein, like you could imagine that like you have a water as well as a air. So you have two phases acting together. When it also interacts with the building or maybe seawall at the coast, like you also have aeration. So you can now realize that like it makes sense to introduce two-phase flow in this simulation. In addition, it is also necessary to use the turbulence model because the inundating seabore have a huge Reynolds number, so of course necessitating usage of a turbulence model. In this specific case, I used the realizable Cape Solon turbulence model, but there are still several turbulence models are available in OpenFOAM. So I do not want to go in detail about OpenFOAM, but I will also like to show a little bit about the numerical domain we chose. So the numerical domain we chose is basically something which is representing our newly constructed dam break setup at IIT Madras, wherein one can store a huge amount of water behind the gate, and um, once if you want to generate the bore, then the door would be like suddenly open, and the dam break surges the inland and then interact with the structure behind. So these are all some conditions which I use for the numerical domain. So which is, I think I do not know need to go in detail into it. And I placed the recurve wall and the vertical seawall in front of the building or maybe the structure. And I also varied the distance between the vertical seawall and the building in order to understand what is the minimum distance which I have to first keep my building behind the seawall in order to protect my structure a little bit a better way. So before starting, when you speak about numerical models, so like people always think about whether our numerical model is sufficient enough to capture the real physics. So that means like you first need to validate your numerical model. So I chose a different, two different validation domains. So one is a small domain by Cliffman et al., wherein he conducted a dam direct edge interaction with an obstacle. So here you could see some nice animation of this interaction process. So herein, like I compared the pressure acting on this buffer, I mean the small block at the top as well as at the frontal face. Also, I compared the water level elevations. So you could see here that like here the dotted line is nothing but the experimental one, and the dashed line is the numerically simulated one. You could see here that like the numerically simulated result more or less matches the experimental results. So with this confidence, I went with the same numerical domain settings to a new domain, which is currently, you could imagine that like here you have a mitigation seawall, so which is the representing what I wanted in this study. And then there is a building behind this mitigation wall, or maybe the vertical seawall. So this represents more or less what I really wanted. So I chose this experimental domain, and here this orange one represents the dam break tank, and dam break tank, and the dam break is allowed to flow, and you could see here some nice flow interaction with the building models here at the different phases of tsunami interaction. First, for example, when the tsunami wave is like approaching towards the seawall, it is deflected directly on the building, and then later like it forms a kind of a transition phase, people usually say, wherein aeration as well as water reactions plays a major role, and then finally you will have a quasi steady flow, which is like more or less kind of a steady inundations. So in order to effectively first effectively say that like my prediction is working fine. So I compared the force time history measured in the experiments and the numerical domain. So you could find here that both the impact phases and the transition phases as well as the quasi steady phases are captured more or less fine. So so by that way, now I validated my numerical settings. So this is basically the simulation protocol. The highlighted colors here in the green, which are nothing but I hereby say they are small sea walls. So the sea walls which have a height, which have a smaller heights, and then from wall 4 to wall 5, I say here as a medium height seawall, and wall 6 and wall 7, I say here as a large seawall. And I conducted experiments with the two different impoundment depths. Impoundment depths, I hereby mean that the height inside the dam break tank. So also I varied the distance between my seawall and the structure, and I tested for two different configuration. One is vertical wall, and vertical wall with a RICO on the top, which is represented as LRC. So when you think about a vertical wall with a RICO on the top, so people should also imagine about the size of the RICO. So which is in general not yet finalized. So that means like we have to choose a realizable value. So I chose the realizable value of a 0.305 based on our previous experiments with normal wave interactions. So in future I also focused on trying to understand how different sizes of RICO influences the forces on the building, but I will show a little bit later. So herein I non-dimensionalized the height of the seawall presented here with this equation h of wall equal to h 1.3 fr plus 1, which is here nothing but the minimum height of the seawall required for the waves not to overtop. So I need to have minimum of this much height in order to say that like my seawall completely, reflects the incoming tsunami core without allowing any overtopping. So I non-dimensionalize it so that like you can now realize that in this case 0.16 means my height of the seawall is just 0.16 times the minimum height required for the waves not to overtop. So by that way I tested for different overtopping conditions, as you could see here. So now let's also check. For example, this domain is like completely new. Although like I validated my numerical domain, I also need to first conduct some mesh sensitivity analysis. So I tried with the different mesh settings, and you could clearly find, especially during the impact phase, like there is a large problem, because the problem here is like the flow is getting thinner and thinner when it approaches the coast, because I made the tank as like 9 meter away from the recurve wall, so my flow would be thinner and thinner, as you could see in the next simulations which I would show. And but in the case of other phases of forces, for example, during the continuous bore inundation of tsunami, I can imagine, you can clearly observe that like there are not much variations in the settings. I mean, much variations in the forces. So I choose this fine setting. The fine setting is something like which I showed here, the numerical domain details here. So, in addition, I also focused on understanding the effect of recurve sizes on tsunami forces, because this is something really important, because we currently do not have any knowledge of how much the recurve size would be. So I tested with different recurve sizes. So alpha here represents the height of the recurve divided by the height of the seawall, and for different conditions. And one important observation I made is like here also only during the impact phases the forces varies, but in the other phases the forces doesn't vary much. So I also started focusing on the quasi steady flow phase, because for the simple reason this is a kind of idealistic condition, but in reality you also have, for example, some behind the sea walls you might have some trees, or maybe some service roads, or maybe some bridges which would obstruct the initial impulsive force, but not the quasi steady phase. So my study was completely on this specific region between 15, I mean between 16 to maybe 30 in the non-dimensional time space. And let me go to quickly the results and discussions. So I hereby also present a nice simulations video with the recurve and the vertical wall. You could find here that with the help of a recurve, what happens is like the incoming wave is like kind of reflected back into the sea. But in case of vertical wall, like the wall first deflected the incoming tsunami bore kind of a splash up, and then the splashed up core falls on both the side and interacted with the building. And you would have also identified, for example, in the case of a vertical seawall with a recurve on the top, the time of interaction with the building is kind of reduced, increased compared to the vertical wall. So the vertical seawall did not reduce the time significantly. So that is something what you could also observe here. LRC is represented with the red line, and gray line is with the vertical wall, and the black solid line is nothing but in the case of no wall condition. And you could clearly identify here that like the forces are getting really reduced by having a vertical wall. Here in the vertical wall height is like wall 4 in d naught equal to 0.9 meter. So that means the height of the wall is nothing but 0.38 times the minimum height required for non overtopping. So even in the medium wall conditions, it was able to significantly reduce the forces on the building. So the time of interaction, so which is something really important. So when you have a seawall, you will also have a false sensation that like the seawalls would first increase the time for evacuating the people. But in the case of vertical wall, you one could clearly find that like even with the increase in the height of the seawall, there was not much increase in the time period for people to evacuate. So but in the case of a large recurve wall, so you could find here that with the increase in height of the seawall, like one could find that like the time period of interaction with the building, so which indirectly says a larger time period for the people to escape. So so that means here you could partially imagine that like this LRC is performing better than a vertical wall, as you could as you could find here in terms of time of interaction. But as I also said, like I varied the length distance between the building and the seawall, and also I varied the height of the seawall. At first, I tried to identify the effect of the distance between the seawall and the building, and you could identify especially for the smaller height seawalls, like the reduction of forces was not so appreciable. So herein I non-dimensionalized the forces by no building conditions, and you could identify that like only like 4 to 5% reductions in the case of even LRC. But when you keep it far away, here in L represents the distance between the building and the seawall. When you keep it far away, even the same building, I mean same seawall height, was able to reduce the force by 20%. So that means like you could now imagine that like you need to set up a minimum distance in order to enjoy the benefit of a seawall. But with the large height seawalls, for example, this effect was not so predominant. So that means like the effect of the distance between the seawall and the building is plays a major role only in the case of low-rise seawalls. Similarly, it was also observed in the vertical wall, and here you could observe that like in fact no reduction in the force was observed for the low-height seawalls. And in some cases, like I observed that the overturning moment was in fact higher than the no seawall condition. So that means it is performing negatively. But that's why like we have to keep a minimum distance between these two. But besides that, like I try to also arrive at some empirical equations for the designers, so that like they can use this for designing the coastal building in future if they have a seawall in front. So herein the force has been similarly non-dimensionalized with no building, no seawall conditions, and for the varying height of the seawall, and one could find that like the forces more or less linearly decreases with the increase in the height of the seawall. In the case where the distance between the small seawall and the building is not so appreciable, like the forces in fact were not even reduced. And similarly for the overturning moment, I propose some empirical equations. So I know that like now I have been speaking for so long time, but I also wanted to now have your opinion, like which one do you think is performing better, whether the vertical seawall with the recurve on the top or simply the vertical wall.
So from the audience, I would hear like it's vertical recurve wall that is functioning better, sir.
Okay, nice. So let us also try understand what happens like when you or what happens exactly on the seawall. So now we understood the effect of seawall in reducing the forces on the building. Let's also try to improve our understanding on the seawall itself. So before I go a little bit in detail about this interaction, so as I said, like when the bore interacts with the seawall, you initially have a bore impact, and then there is a reflection phase happening, and then continuous quasi steady force applying on the seawall. In fact, it is the same for the building too. Let's try to understand also some pressure time histories on the vertical wall. Here in the wall 4 is represented, which is the medium height seawall for a water depth impoundment conditions of 0.9 meter. So I hereby find this. I mean, the black lines are nothing but the vertical wall, and the red lines are nothing but the recurve walls. So here I could find that like in the case of lower depths, so the section 1 here, the impulsive forces and the quasi steady forces are like more or less the same for both the vertical wall as well as the recurve wall conditions. In fact, like even at location 2, I find that like the vertical wall is like kind of a slightly experiencing higher pressure, but not so significant compared to the recurve wall. But when you go up towards the recurve, you could identify that the recurve is experiencing a significant pressure. So that means like your recurve portions are the portions of high vulnerability or high risk of failure. So 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 let us also try understanding the horizontal forces acting on the seawall itself. So for better understanding, I also present here the time. I mean the pressure over the entire depth of the seawall. So the red lines here are with the vertical wall with the recurve on the top, and the black lines are the simply the vertical wall. And you could find here that like this is for three different wall conditions: wall 1, wall 4, wall 7. So you could identify here that like the LRC is experiencing a significant forces on the horizontal direction for all the three seawall heights. But when you also increase the height of the seawall, the difference between the forces acting on both of them are not so appreciable. But in the case of low rise seawalls, the LRC is experiencing a significant force, especially during the initial impact. And in fact, it was also the same observations made for the medium height seawall. So that means here, simply you could understand that like the forces on the vertical wall with the recurve on the top is like maybe 1.4 times higher than the vertical wall itself. So that means LRC is experiencing a large force in order to reduce the forces acting on the building behind. But you could also recollect a little bit that like the reduction in the forces between the LRC and the vertical wall was not so significant. Of course, LRC was performing a little bit better, but not so significant. But the amount of force which it experiences itself is really, really high. So in fact, you could observe here that at the recurve portions especially, the pressure is like really, really high compared to the vertical wall wherein the pressure is really low. So in addition, like you could also observe here that like in the case of a low rise sea walls, you have maximum forces during the impulsive force stage. But in the case of high rise sea wall, like you have maximum forces during the quasi steady flow phase. So that means I also need to identify why it is happening such a way. So that's why like I plotted here some of the flow interaction processes in the quasi steady flow phases especially. Here you could identify that like with the increase in the height of the seawall, the water level differences between the frontal side and the back side is like getting larger. So that means you have a large pressure acting on the vertical wall or a vertical wall with a recurve on the top when you have a larger weight, larger height. But in the case of low rise wall, like it is completely over up. So the pressure acting on the frontal side is compensated by the backside pressure. So you have only hydrodynamic forces happening on the low rise seawall. So that was the reason like why this kind of seawalls, small rise seawalls, experiencing the maximum forces during the impulsive force stage. In addition, like I specifically wanted to mention for the overturning moment on the uh, recurve wall and the vertical wall, here you could identify that like the overturning moment is like increased almost twice for the lower IC wall compared to the high IC wall. Like of course, like it is more or less producing the same results, but in case of lower IC wall, like LRC is experiencing a significant overturning moment. But in addition to it, the LRC has some projection. This recurve has some projection. So because of this projection, there is also a uplift force happening on the recurve. So I also plotted some of the uplift forces that are happening for different height of the seawall. You could identify that with the increase in the height of the seawall, the recurve wall is experiencing more uplift force during the quasi steady flow phase. But with the further increase in the height, like the forces are once again getting reduced. This is because it has a strong correlation between the overtopping volume. For example, when you have a very high rise sea wall, then the forces acting on the recurve portion is also getting a little bit reduced. And that's why like we are experiencing a little bit less of forces on when you go for very high rise sea walls. And in addition to it, like I also try to identify whether since because when you increase the height of the seawall, I also increased the recurve sizes proportionately. So that means my recurve size is also increasing. But for one specific case, I tried to understand how this recurve sizes alone for a single vertical wall really matters. So as I explained previously, like I chose four different ratios for the recurves, but in specific, I observed that like in the case of horizontal forces and overturning moment, the recurve sorry, the recurve did not significantly increases the forces, but the recurve itself is inducing some additional forces. And when it comes to vertical uplift forcing, the with the increase in the recurve sizes, my forces is also increasing. So when you are choosing a recurve wall, one should be really really careful about the size we chooses. So the least one should be adopted. Of course, like one cannot only design the seawall only for the extreme conditions. For the normal conditions, like people also need to evaluate like this recurve sizes, which has not been evaluated until as of my knowledge. So this uplift force is directly proportional to the recurve size. So now the same question, like which one is performing better? As an engineer, like which one you would choose?
Sir, it's the same like recurve wall, but with like minimum size. Like.
Yes. To be also on the safer side, like when you also have a little bit higher rise, higher sea walls, so we could still prefer a vertical wall alone, because the recurve anyway, because of this horizontal, I mean, because of the projection from the recurve wall, like it experiences some uplift forces, of course, which is which is a kind of destabilizing force for the structure. In fact, even during the past tsunamis, what they observed after the field surveys is like the vertical seawall with the recurve on the top is experienced larger forces, and because of that, like a part of the seawalls, for example, the recurve portions were like completely, detached from the vertical seawall, and was transported. So so one has to be really really careful when choosing the size of the recurve, especially in areas when where the tsunami is like more prone. So some key conclusions, but of course, like it is, already now that with the height of increase in the height of the seawall, the forces of course reduces, and it also depends on the flow properties. And you observe that like there was a linear reduction in the forces on the building, and a non-linear reduction in the overturning moments. And a low-rise vertical seawalls actually experiences sometimes vertical seawalls actually have a negative effect, because when you keep it very close to the building, like sometimes the building experiences more forces than without seawall conditions. So as an engineer, like one has to be really really careful when you are designing a seawall, especially for tsunami like conditions. And vertical seawall with the recurve on the top actually has a more probability of failure because of this horizontal projection. So sometimes this could, give a false impression to the people or maybe the engineers that with the recurve, like it is more efficient in transferring back the incoming wave, but it is not, especially in the case of tsunami like conditions. So in addition to that, like I also focused on understanding how vegetations and vegetations efficiently reduces the forces on the building. In fact, like I also published it in a conference work. And the next step, like I still want to focus on, is understanding how sea walls and vegetations together could reduce the forces on the building. In fact, this specific video I really wanted to show, because like this is an experimental video, and which has been conducted in our institute in Aachen. And these are all some publications which I have it in terms of tsunami structure interaction. Of course, my entire PhD was on tsunami structure interaction, so I had a large number of publications uh, on this specific topic. And I would like to here once again say thank you all for listening. Of course, I can understand that it was an exhaustive literature, but exhaustive work. But yeah, thanks again for your time and your presence here. And if you would like to maybe follow me on some social pages, here is my LinkedIn ID. So you could join with me maybe in future if someone wants to progress their career in research. Like I would be more interested to guide. And yeah, of course, for the publications related things, like you could refer to my research gate page. And yeah, thank you again once again. So I
Thank
stop
you.
here.
Thank you so much, sir. Thank you so much for the informative session. So, can we have few questions, sir?
Yes, of course. Yes,
Yeah,
of
sure.
course I will.
So, any questions? Sir, one of the question is like how the water flow will be after construction of the seawall, sir.
Uh, After, I mean, after construction of the seawall, in the sense like regarding the flow characteristics, or
Yes, sir. Regarding the flow characteristics.
so in fact, like I still did not work specifically on this. I mean, I have some data, but I still did not convert it into some good graphs, or maybe to have a better realization. But until my analysis, understanding, and previous literature, so when you have a vertical seawall, then what happens is like, of course, what, just imagine of a seawall. So what happens is like you have a reduced bore depth behind the seawall when compared to no seawall conditions. So that is something like which is which make people also really happy, because one can easily escape in water depth maybe of 1 meter, but just imagine a water depth of a 3 meter, which is approaching towards you. So with the help of a seawalls, like you have a better reduction in the bore depth, but of course there will be an increase in the flow velocity because of this flow overtopping, depending on the type of seawall. For example, at some coasts you would also find some trapezoidal type seawalls. In that case, like the shape itself promotes increased flow velocity. So several factors plays a role. In fact, one of my master student is currently working on identifying different type. I mean, identifying the flow features behind the different types of seawall, wherein he also focuses on vertical seawall with the recurve at the top, a trapezoidal type seawall, and then a complicated curved seawalls, for example. So, but overall, something for people is like when you have a recurve wall, or when you have a mitigation wall or a sea wall, you will have a reduced flow depth. So that is something advantageous, and sometimes there might be an increase in the velocity or decrease in the velocity depending on the features behind the seawalls. So in reality, you also have some vegetations or maybe some obstructions in terms of service roads, for example.
Yes, sir. There is like one more question.
Yes.
Some cases should not construct the seawall is better. Sir has told you. What is that condition?
Certain circumstances, it would not be advisable to construct a seawall. Would you like to elaborate a few sentences over it, sir? Like few points on it?
Yes, yes, of course. It is especially true when you have I mean, for example, when you have a buildings. Uh, just imagine our Chennai coast. There are some places in the Chennai coast, like where the buildings are constructed very close to the shoreline. And in this case, just imagine that, like, if you want to protect it by using a small seawall at least. So there are not sufficient spaces between I mean, there is no sufficient space between the building and the incoming building and the shoreline. So also, people would not also advise to go for like 10 meters seawall, 12 meters seawall everywhere. So of course, like there will be a minimum restriction that like you have to construct like this much amount of seawall. One, if someone knows about the incoming bore depth from some analysis, and based on the incoming bore depth of the tsunami, you could identify the height of the seawall. I mean, you could identify the non-dimensionalized height of the seawall, that is, which is something I told you already, which is the height of the seawall divided by the minimum height required for the for topping. So if that height is, if that ratio is falling lesser than maybe 0.2, then what happens is like if you have a seawall very close to the building, then it would go. I mean, it would be a negative influence on the building behind rather than having a positive influence. In fact, during the initial splash up, sometimes what happens is like they splash the bore directly fall on the maybe the second floor on top third floor of the building. So that means this impulsive force is directly acting on acting at a higher height, so which also induces a large overturning moment acting on the building. In fact, that's what I also showed here. Maybe I'll also present once again.
Yes, sir. Thank you. Is it
So
okay?
this is the one, like here, like in the case of very closer sea walls, then the forces are in fact going really high, and sometimes it is also exceeding compared to even low seawall conditions. So in these cases, it is better to avoid any construction of seawall.
Okay, sir. Is it fine? Can we go with one more question?
Yes, yes, of course.
Um, can you suggest a code book for designing, sir? Code.
Okay, so code book for designing.
Using materials also.
So until now, to my knowledge, like in India, like we have some code books regarding the tsunami interaction with the shorefront structures, for example, the port structures, and wherein people normally uses the hydrodynamic force equations, which is you might know already based on, I mean, which is force is equal to half rho h u squared, which is the hydrodynamic force. So people suggest using that formula for estimating the forces on the building. but there are no well established code books. But when you go for some foreign standards, for example, American standards, it is called ASCE 07, which is explicitly speaking about minimum loads acting, minimum design requirements for tsunami loads. And there is also one more guidelines from FEMA. So you that is also providing guidelines for designing buildings at the coast. And as you might already know that like Japan is suffering from tsunamis or frequent intervals, they do have internal codes. But even in those codes, like they suggest going for hydrodynamic force equations for estimating the forces on the building.
Yes.
But in the case in our Indian standards, we at the moment, in fact, like based on my PhD work, our professors suggested some design equations for the constructions of the course. So it is not yet actually available now. So it is sent to them, but it is not yet available for public.
Oh, okay, sir. Like, that's fine. Like, one more question is like, based upon materials, like whether it is pre-stressed or like other kind of environment, or like based upon materials, is there any code that is defining?
I think for that, I guess like we could go for some code books which speaks about port and harbor structures. I could not clearly remember the code book number. I'm not sure 4651 or something like that. I do not remember exactly. But when it comes to material, like we could always refer that specific code books like for port and harbor structures. There are some 5 series of such a book, so you could refer that for the materials especially.
Yes, yes, yes. Thank you, sir. Sir, the next question is like on the numerical modeling point of view, whether the mesh is
Yes.
structured or unstructured.
Actually, the mesh is kind of unstructured, but it is still hexagonal mesh. So in the sense, like since the domain is like really really long, so it is like of a 25-meter long and 1 meter wide, 1 meter height. And in order to precisely capture also the thin phases of flow, so I had to stretch meshes at some places, especially inside the tank. I stretched the mesh so lot. In fact, like I can show you this one too. It is on my slide already. That's actually a good question because choosing mesh size is like something really really important. Otherwise, like we will end up in some computational domain which is of a really computationally expensive, especially when we speak about Reynolds average Navier-Stokes equations. For example, in the x direction, I chose 4 centimeter inside the tank and also varied from 4 centimeter to 1 centimeter towards the structure, because especially in this portion you could also, you would also seen in my simulation video, the bore front is like going very thin. In order to capture that, like we need to have a smaller size mesh. And in the z direction I kept the mesh size to be constant, and the y direction similarly on the y direction, since my building is of my primary importance, I chose 1 centimeter at the center of the flume, and towards the edge of the flume I chose it as 3 centimeter, because I really wanted to capture the process happening at the structure more precisely. So but nevertheless, I arrived at this numerical domain details and the mesh details based on previous studies. So wherein people use this stretching technique to model some precise flow features, especially near substructures.
Thank you, sir. Thank you so much, sir, for your time. Like, the session actually highlighted all the important aspects of like waves, extreme wave impacts, sea walls, tsunami wave forces on buildings, and like on the recurve walls and sea wall point of view, sir. So like, thank you so much on behalf of Institute of Ocean Management and on NWS EIACP Center. We would like to thank you for sharing a session over here, and I think like it could be beneficial for the students in carrying out their project works. Thank you so much, sir. Like, I would request everyone to on the video mode so that like we can have a group photo. So like, is it fine, sir?
Yes, completely fine.
Yeah, yeah.
Also, I should definitely thank you because for arranging this webinar, and I'm really happy to deliver some speeches in Hana University because I remember I remember yeah, I remember that during 2012, like I was at Hana University for my bachelor's, choosing of a college in bachelor's. I was at the time little bit, feeling a little bit sad because I couldn't study in Hana University at the time. But at this moment, I'm really happy that like I'm kind of honored to deliver some speeches in front of you. So I should really thank you for inviting me to this lecture series.
Thank you, sir. Thank you. Thank you. Pleasure is ours. Everyone, kindly on your videos. It. Thank you. Thank you all. Yes, sir. Like we would let you know if we have further questions on it, sir. We
Yes, of
communicate
course.
with mails. Thank you, sir. Thank you,
Thank you
sir.
very much.
Yes.
Thank you, sir. Thank you, sir.
Thank you all.
Yeah, maybe if someone needs any guidance, they can also just write me on LinkedIn or maybe on my to my email. So I'd be happy to help you. Thank you.
Sure, sure. Thank you.
Shall I leave?
Yes, sir. Yes, yes, yes.
Thank you.